Welcome to Chapter 6, Gas Metering and Measurement. Accurate measurement is the key to revenue, safety, production optimization, and regulatory compliance. Every cubic foot of gas must be measured correctly to ensure fair transactions and efficient operations. In this chapter, you will explore the principles of gas metering, understand common measurement technologies, and learn how engineers use measurement data to make critical operational and business decisions. Because in the petroleum industry, what gets measured gets managed. Why is gas measurement so critical in petroleum industry? Because every business decision begins with an accurate measurement. Gas metering determines how much product is bought and sold, ensuring fair custody transfer between producers and customers. It also forms the basis for royalty payments, taxation, and production allocation among partners and facilities. Beyond economics, accurate measurement supports safe and efficient pipeline operations by helping engineers monitor flow, optimize performance, and maintain system integrity. The impact of measurement accuracy is enormous. A 1% error in a gas stream of 300 million standard cubic feet per day can result in more than $1 million per year in lost or misallocated revenue. The message is simple: every unit counts. Accurate measurement protects revenue, improves safety, ensures compliance, and delivers value across the entire petroleum industry. There are 4 challenges in gas measurement. First, pressure affects volume. As pressure increases, gas is compressed and occupies less space. As pressure decreases, gas expands. Second, temperature affects volume. Warmer gas expands, while cooler gas contracts, changing the measured volume. Third, natural gas does not behave exactly like an ideal gas. Compressibility effects become significant at high pressures and must be accounted for using correction factors to ensure accurate measurements. Finally, all gas volumes must be converted to standard conditions so that measurements can be compared consistently across facilities, pipelines, and commercial transactions. The key takeaway is simple: pressure, temperature, and compressibility all influence gas volume. Accurate gas measurement requires correcting for these effects to ensure fair, reliable, and compliant operations. Gas flow meters can be classified into 4 main categories based on how they measure flow. Differential pressure meters determine flow from the pressure drop created by a restriction in the pipeline. These are among the most widely used meters in the industry. Velocity meters measure the speed of the gas and convert it into a flow rate. Common examples include turbine and vortex meters. Positive displacement meters measure flow by trapping and counting fixed volumes of gas, making them highly accurate for many commercial applications. Mass flow meters measure the actual mass of gas flowing through the system, independent of pressure and temperature changes. Each meter type has unique strengths, limitations, and applications. Selecting the right technology depends on operating conditions, required accuracy, installation requirements, and economic considerations. The key takeaway is simple: understanding meter classification is the first step toward choosing the most effective gas measurement solution. Selecting the right gas meter is not a one-size-fits-all decision. Engineers must evaluate several factors before choosing the most suitable technology. The process begins by confirming that the application involves gas measurement. Next, we determine whether the measurement is for custody transfer, where accuracy and financial accountability are critical. If high accuracy is required, the next consideration is gas quality. Clean, dry gas may be suitable for advanced meters such as turbine, ultrasonic, or mass flow meters. Dirty or wet gas may require more robust technologies that can tolerate challenging operating conditions. By following a structured decision-making process, engineers can match the meter technology to the application, ensuring reliable performance, accurate measurement, and cost-effective operation. The key takeaway is simple: ask the right questions, follow the roadmap, and select the meter that best fits the process conditions and measurement objectives. The orifice meter is one of the most widely used gas flow meters in the petroleum industry. It operates on the differential pressure principle. As gas flows through an orifice plate, the flow area is restricted, causing a pressure drop. By measuring the pressure difference across the plate, the gas flow rate can be calculated. A typical orifice metering system consists of an orifice plate, pressure taps, impulse lines, a differential pressure transmitter, and a flow computer. Because of its simplicity and proven reliability, orifice metering is commonly used in pipelines, custody transfer stations, production facilities, and compressor stations. Its main advantages include low cost, rugged construction, ease of installation, and widespread industry acceptance. However, It also has limitations, including permanent pressure loss, lower accuracy than some modern meters, and sensitivity to installation conditions. The key takeaway is that the orifice meter remains an industry standard because it is simple, reliable, and cost-effective when properly designed, installed, and maintained. Let's see how an orifice meter is used to calculate gas flow in practice. The first measurement is the differential pressure across the orifice plate. In this example, the pressure drop is measured by a differential pressure transmitter. Next, we record the operating pressure and gas temperature. These values are essential because gas density changes with both pressure and temperature. Using the differential pressure, temperature, and meter characteristics, the flow computer applies the standard orifice meter equations to calculate the gas flow rate. The calculated flow is then corrected to standard conditions, allowing the measurement to be compared consistently for reporting, allocation, and custody transfer purposes. This example highlights an important principle. Accurate gas flow measurement depends not only on differential pressure, but also on reliable pressure and temperature data. These measurements enable engineers to determine flow rates with confidence. The Venturi meter is another differential pressure flow meter, but it uses a gradually converging and diverging flow path instead of a sharp-edged orifice plate. As gas flows through the narrow throat section, its velocity increases and pressure decreases. The pressure difference between the inlet and the throat is then used to calculate the flow rate. Compared with an orifice meter, the Venturi meter offers a major advantage: significantly lower permanent pressure loss. This means less energy is wasted as the gas flows through the meter. Venturi meters are also better suited for dirty, wet, or particulate-laden fluids because their smooth internal profile is less prone to erosion, wear, and blockage. However, these benefits come at a higher cost. Venturi meters are larger, more complex to manufacture, and more expensive to install than orifice meters. The key takeaway is that Venturi meters provide excellent performance with lower pressure loss and better handling of challenging flow conditions, making them a preferred choice when efficiency and reliability justify the higher investment. The turbine meter measures gas flow using a rotor principle. As gas passes through the meter, it flows across precision-engineered rotor blades, causing the rotor to spin. The speed of rotation is directly proportional to the gas flow rate. Sensors detect the rotor speed and convert it into flow measurements, allowing the meter to accurately determine the volume of gas passing through the pipeline. One of the main advantages of turbine meters is their high accuracy and excellent repeatability. They provide fast response to changing flow conditions and are widely used in natural gas transmission, distribution, and custody transfer applications. However, turbine meters require clean, dry gas to operate reliably. Dirt, liquid droplets, and solid particles can damage the rotor or affect its performance, reducing measurement accuracy over time. For this reason, filtration and gas conditioning are often required upstream of the meter. The key takeaway is that turbine meters offer highly accurate and reliable flow measurement, but their performance depends on maintaining a clean gas stream and proper operating conditions. The positive displacement meter measures gas flow by directly capturing and counting fixed volumes of gas as they pass through the meter. Unlike differential pressure or velocity base meters, a positive displacement meter does not infer flow from pressure changes or fluid velocity. Instead, it physically traps a known volume of gas and transfers it from the inlet to the outlet. By counting the number of cycles, the total gas volume can be measured directly. This direct measurement approach provides excellent accuracy and repeatability across a wide range of operating conditions. Because of its precision, the positive displacement meter is widely used in custody transfer applications where accurate billing and revenue measurement are critical. These meters are commonly found in city gas distribution systems, industrial gas supply networks, and commercial metering stations handling low to medium flow rates. The main advantages include high accuracy, reliable long-term performance, and minimal sensitivity to flow profile variations. However, because they contain moving mechanical parts, regular maintenance may be required to ensure continued accuracy. The key takeaway is that positive displacement meters provide direct volume measurement with exceptional accuracy, making them one of the preferred technologies for custody transfer and revenue metering applications. Thermal meters measure gas flow based on heat transfer. They directly measure mass flow and are widely used where low flow rates and high turndown capability are required. Vortex meters operate by detecting vortices that form downstream of a bluff body placed in the flow stream. The frequency of these vortices is proportional to the flow rate, making vortex meters suitable for both gas and steam applications. Magnetic meters use electromagnetic induction to measure flow. However, because natural gas is not electrically conductive, magnetic meters are generally used for liquids rather than gas measurement. Target meters measure the force exerted by flowing fluid on a target placed in the pipeline. They are rugged and can handle challenging process conditions, including dirty or wet flows. Pitot tube meters determine flow velocity by measuring the difference between stagnation pressure and static pressure. They are simple, economical, and commonly used for large pipelines and flow surveys. The key takeaway is that each advanced metering technology offers unique advantages. Selecting the right meter depends on factors such as fluid properties, accuracy requirements, operating conditions, maintenance needs, and overall project economics. The orifice meter offers high accuracy at the lowest cost, making it one of the most widely used meters in the industry. However, it produces relatively high pressure loss and performs only moderately well with dirty or wet gas. The Venturi meter also delivers high accuracy, but with significantly lower pressure loss. Its smooth flow path makes it excellent for handling dirty fluids and wet gas streams. The trade-off is a higher purchase and installation cost. Turbine meters provide very high accuracy and excellent repeatability, making them popular for custody transfer applications. However, they require clean, dry gas because dirt and liquids can damage the rotating components. Positive displacement meters also achieve very high accuracy through direct volume measurement. They are widely used for revenue metering and custody transfer, but their moving mechanical parts make them less suitable for dirty gas streams and can result in higher pressure loss. The key takeaway is that no single meter is best for every application. Engineers must balance accuracy, cost, pressure loss, and fluid conditions to select the most appropriate metering technology for a given operation. Gas metering plays a critical role across the entire petroleum value chain. Different applications require different metering objectives, but all depend on accurate and reliable flow measurement. In well testing, gas meters measure flow rates and total produced volumes to evaluate reservoir performance, productivity, and well deliverability. For production allocation, metering data is used to fairly distribute production volumes among wells, assets, or joint venture partners, ensuring transparency and accurate revenue allocation. Within gathering systems, gas meters monitor flow through collection networks, helping operators detect imbalances, identify losses, and optimize transportation efficiency. At custody transfer points, metering accuracy becomes commercially critical. Measurements determine the quantity of gas being bought and sold, requiring compliance with industry standards and regulatory requirements. In gas processing plants, meters track feed gas, product streams, and fuel gas consumption, supporting process control, accounting, and plant optimization. The key takeaway is simple. Selecting the right gas metering application ensures accurate measurement, operational efficiency, regulatory compliance, and revenue integrity throughout petroleum operations. Let's apply meter selection principles to a practical field case. Our scenario is a gas well producing 10 million standard cubic feet per day, or 10 MMSCFD. Before selecting a meter, engineers must answer three critical questions. First, is the gas clean? Clean, dry gas with minimal liquids and solids allows the use of high-performance meters that rely on stable flow conditions. Second, is the measurement for custody transfer? If the measured volume will be used for commercial transactions and revenue calculations, high accuracy and industry compliance become essential requirements. Third, is sufficient pressure available? Some meter technologies require an adequate pressure differential to achieve their specified accuracy and performance. In this case, the answers are yes to all three questions. The gas is clean, custody transfer accuracy is required, and adequate pressure is available. Therefore, a turbine meter is an excellent choice. It provides high accuracy, proven reliability, low maintenance requirements, and is widely accepted for custody transfer gas measurement. The key lesson is that meter selection should always be based on process conditions, measurement objectives, and operating constraints, not simply on flow rate alone. This chapter presented gas metering and measurement. We began by understanding why accurate measurement is essential for operations, revenue, and regulatory compliance. We then examined the key challenges affecting measurement accuracy, including pressure, temperature, gas composition, and flow conditions. Next, we reviewed the major gas meter types and their operating principles. We also learned how to select the right meter based on process conditions, accuracy requirements, and operational constraints. Finally, we explored petroleum engineering applications. The key takeaway is simple. The right meter in the right application delivers accurate measurements, reliable operations, and better engineering decisions.